Today we will be beginning Unit 3, which is titled Waves. Let me just put in the heading. Okay, there we go. And within this unit, we have 4 topics. We're going to talk about general properties of waves, which is something I hope to cover today. Then we will focus on light, and so there are a few chapters within that topic. Then there's the electromagnetic spectrum, or the EM spectrum, electromagnetic spectrum, which includes light, and then your X-rays and UV and IR and all of those. And then finally there's sound. And so starting today with topic 3.1 is the general properties of waves. So, right, as the topic tells you, we're going to talk about things generally, and we're just going to introduce certain concepts and certain terminologies. We'll go into details of those when we talk about light in particular, and then the electromagnetic spectrum later on, but mostly when we're talking about light. And then sound, obviously, when we talk about longitudinal waves, so that's something I'll talk about. And so it's, as you would expect from an introductory topic, there is going to mention things and move on without really going into detail about how that happens, right? So let's get started with this. The first thing they mention are mechanical waves. Right? And these are waves that are produced by a disturbance, such as a vibrating object. And it happens in a material medium. Material medium meaning matter, right? So you need matter to be present for these waves to occur. And they are transmitted due to the particles of the medium that are vibrating about a fixed position. Right, now examples of what what types of waves are included in mechanical waves. One are water waves. So you've already, we've obviously seen those, hopefully.
Yeah.
And the other are sound waves, which we haven't seen. And with this, we get right, we also get to know that along with the classification of waves as mechanical, and then the other one that we'll talk about are progressive waves, right? Water waves are the way in which they travel are transverse, not longitude. They
Uh,
are
so like,
they are
so like,
transverse. Yes, please.
so like everything moves in waves.
Everything does not move in waves. The way, right, certain in certain things, right, energy is transferred in the form of waves.
Okay.
Right, and sound waves are longitudinal. We talk about what the difference between those two are, right? So this is you know, their the, the way they move. Next up are progressive waves. And these, right, progressive waves are also called traveling waves. And you know, they travel at right angles. The direction of their movement is at right angle to the disturbance.
Okay.
Along with that, right, so direction of movement is also called direction of propagation of wave. And right, they move without a transfer of matter. So they carry energy without, you know, any matter being involved, without transferring matter. And examples of progressive waves are waves of the electromagnetic spectrum, which include light, right? Because they can travel so without, they can travel in vacuum where there are no air particles or anything else. So they don't need material for them to move. Whereas water waves, water is matter itself, right? Sound needs matter to travel, and that's why sound does not travel in vacuum. So in space, you cannot hear sound. And that's one of the reasons why, right, you don't hear the explosions going off in the sun. You just get the heat, which is infrared, which is part of the electromagnetic spectrum, and you get light, which is also part of the electromagnetic spectrum, which are both progressive waves, right? So they don't need any matter. Whereas sound needs matter, and so there are explosions happening in the sun, right? All the, the nuclear fission and fusion, whatever's going on over there, but you don't hear any of it, because if you would be able to do that, it would be very loud and horrifying.
What is meant by electromagnetic spectrum?
we'll talk about that, right? So we obviously have an entire chapter, an entire topic about that, right? And so it is, right, a certain set of waves uh, of certain properties within that spectrum. So you've got X-ray and UV and IR and light, right? And then radio waves that come later on. And so they have different frequencies, different wavelengths, certain properties, and a common property for all of them is that they do not require matter. They all transfer energy, but they do not require matter for that. So again, they can move in vacuum, right? And so they are also pretty fast.
And like, can you explain progressive waves again?
So, right, you've seen, again, you've seen water waves, and right, you've seen how, right, you probably only seen this part of the wave, right, the one that comes on top. But waves move like this, right? And so when you see waves in the water coming after one after the other, right, you all can also see videos from of a wave from under the water, and so you would see this part. It's beautiful and scary at the same time, right? So this is happening obviously because it's under the surface. You can't see it, but it is happening. You only see when the wave rises up. And so, right, this is a mechanical wave because it involves matter, right? So water is obviously H2O. It is a physical substance. It involves matter. Whereas a progressive wave is also the same, and this is, right, a transverse wave. So we'll talk about that, right? Progressive waves, as we've talked about EM spectrum, they are transverse again, and the only difference is that they are basically energy, right? They're basically energy traveling at different speeds. So you might have a wave that's traveling really fast, and compared to that, you might have a wave that's traveling a bit slower. Now, again, right, just that diagram won't make much sense. We'll talk about frequency and wavelength and, you know, all of that. But they're all just energy. They do not require material for movement. So that's a progressive wave. I don't know if that does that help any in your understanding?
Yes.
No,
No?
no.
Okay, so then I'll just have to ask you to wait until we get to, that topic.
Okay.
So, right, a transverse wave, as mentioned, with the progressive wave, the direction of disturbance is at right angles to direction of propagation. Rewrite that over here. And propagation means movement. And an example of this, something that you can do at home, you can take a rope or, you know, a shoelace, perhaps, although shoelaces aren't very long. So you can take some sort of rope or maybe, a dupatta, if it's long enough, although it's not heavy enough for this. If you have like a light chain, and you can obviously look it up online, like a video. So, and what you can do is you can attach the rope to one end, maybe the handle of your wardrobe or a bedpost, and you can attach the rope over here, and right, that's you, and you're holding the rope, and what you want to do is you move the rope up and down. And maybe this is something that you've tried. So you're moving the rope up and down, but what you're noticing is that you're noticing this pattern in the rope. So your direction of movement, the direction of disturbance, is up and down, but the direction of the movement of the wave is towards the bedpost or wherever you've attached the rope, right? And so the direction of propagation, which is direction of wave movement, it's moving this way. So you will notice, right, this goes up, and then you'll see how it travels, although you're moving it up and down. And so those are at right angles. And when a wave has this particular property, when its movement is in this particular fashion, it's called a transverse wave, right? Whereas if you take a spring, right, now in a spring you can do both. You can do the same thing with a spring as well. So this is transverse, and I don't know if you ever played with those. If you've played with a slinky spring, those colorful rainbow colored springs that come as toys,
Yeah.
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 And so
Yeah.
you've probably tried doing this with those, right? So if you've done that, you can use that to produce a transverse wave as well. Another thing that you can do is, right, and with a spring, you can hold both ends, or there are two people, right? Or it's just you with both, stretching it out with your hands. And one is again trying the transverse thing, and the other thing is that you push it back and forth. So the direction of movement is back and forth. And so what you would notice is that the spring sort of stretches in certain areas, and then it condenses, and then it stretches again, and then it condenses, right? Then it stretches again, and then it condenses, right? So hopefully I've made it, so you have this area where it's stretched, and you've got, right, perhaps this area where it's compact, compressed. So compact. And so in this case, right, with a longitudinal wave, this is called a longitudinal wave, right? And this is also a mechanical wave. Again, right? So Haram, you're using a rope. Is rope made of matter? Yes,
Yeah.
right?
Yeah.
Water is made of matter. Spring is made of matter, right? So it's made of the elements, right? So, right, it's made of the elements, right? It's made of some substance, some material. And so if it helps with the explanation that you asked for earlier, right, a mechanical wave, for a mechanical wave to be produced, to travel, to exist, it needs some substance or some material for to travel. Whereas a progressive wave is not made of any material, nor does it need material to travel. Right? So as I said, it's just energy. So, right, what is light made up of? Is it made up of, some element? It's not made up of any element. It's just, as we
No.
it's just packets of energy. Now I understand that's a vague concept, but that's what light is, right? It's just energy that is traveling. Okay. So we just talked about radiation in.
And like
I'm
I have a
sorry,
question.
your voice is breaking up. I'm sorry. Could you repeat that?
I was saying that I have a question. Like it might sound a little dumb, but
I'm sorry, your voice really broke up. You could try repeating that, or you could put it in the chat. All right, so I'll read it out.
I was saying that
No, I'm sorry, right? It's really breaking up, right?
I have
It's not your fault. It's probably the connection, but
a question.
yeah, I can't make sense of whatever you're saying because of the disturbance. So please type it out, and I'll try to address it. Sorry about that. It's probably the connection. As soon as you start speaking, your voice breaks up. So in the meanwhile, right? So progressive waves are they are not made up of matter, and they do not need matter to travel, but they do transfer energy. So I was referring to radiation that we talked about in the previous class. Uh, right. So radiation is, as they mentioned, it is infrared, right? It's heat energy that's given off as infrared radiation, and so that infrared is part of the electromagnetic spectrum. So right, it's given off. And why is it heat? Like, why is it infrared? So that is a part of the electromagnetic spectrum that has certain properties of their wavelength and frequency and everything, right? And one of the properties it has is heat, right? So right, it has no matter associated with it. So matter can give off heat energy in the form of, it can also transfer heat energy from particle to particle. So we talked about, right, conduction and convection. But then it can also give it off as IR, infrared, which is part of the electromagnetic spectrum, which is progressive. It's not made up of any matter now, right? Again, I hope that helps with the explanation. So right, a longitudinal wave, and like, have you typed it out? Yes.
She didn't.
Right, you have a question. What? Okay, she's gone.
Yeah, yeah,
Okay, unfortunate. In fact, I think her connection gave up midway, because even her question
yeah.
is incomplete. Okay, so we'll see if she can join back, right? Obviously. So I was mentioning longitudinal wave, right? And a longitudinal wave is one where the particles, so the particles of the transmitting medium, vibrate back and forth, just like I, pointed out over here. That's the movement that you would expect. So they vibrate back and forth, right, along the same line as the wave is traveling. So the right, the direction of propagation. And so if we revert this, the direction of disturbance is parallel along the same lines, meaning it's parallel to the direction of propagation. If we just revert that for longitudinal waves, the direction of disturbance is parallel to the direction of propagation, right? That's how we would say it for a longitudinal wave. Another example, uh, for uh, these longitudinal waves are sound waves, and again, right, so sound is something we will come to later.
Yeah. Okay.
Okay, now, right, waves, if you have a transverse wave, so again, right, so let's start from here, and it's going up and down and up and down. I'm not making this very well, I understand that. And so the part that is, at a high over here, this is called a crest. And the part down here, which is at the low, it's called a trough. Okay. The
Yeah.
right, the distance between two consecutive crests or two consecutive troughs, so either one of those, is called the wavelength. Okay, so what's the wavelength of the wave? It is the distance between two consecutive crests or two consecutive troughs in a transverse wave.
Yeah. Okay.
And if I just draw a dotted line over here, the maximum displacement of the wave from the mean position, right? So this is like point 0, let's say, right? The wave is starting from here, it's coming back to 0, then it's going to a trough, then it's rising again. And so the maximum displacement is called the amplitude. Amplitude, not amplitude, right? Not aptitude. Let me write it out more clearly.
Okay.
Amplitude.
Got it. Yeah.
Okay. Now
Yeah.
this is for a transverse wave. In case of a uh, longitudinal wave, right? So you have this a bit spaced out, then you've got this, right, a bit close together, then you've got it spaced out again, and then back together, close together, and then spaced out again, right? So this part, which is all spaced out, is called, right, again, right, so this is a longitudinal wave. This is called a rare fraction, sorry, rarefaction.
Okay.
Rarefaction, right? So
Yeah.
where the matter is further apart, and then this part over here,
Refraction.
rarefaction,
Yeah.
rarefaction, rarefaction,
Yeah.
right?
Okay.
And the part where the matter is close together is called a compression.
Because it's compressed together, right?
Yep, it's close together. And so this part over here is called a compression. The part where it's spread out is called a rarefaction. Okay. Now, right, you don't have crests and troughs over here. So in this case, you don't have an amplitude to talk about, but you do have, right, so the distance between two compressions or two rarefactions, for example, right? So either these or these. So you've got, right, or these two, either of those two, right? The distance between those is the wavelength.
Okay.
Right, so transverse waves have crests and troughs. Longitudinal waves have compressions and rarefactions. Both of them have wavelengths, right? And right, transverse waves also have an amplitude, right? These longitudinal waves don't have amplitudes.
Okay.
Okay. Now to put that in a more formal way, right? Let me write these out over here. So wavelength is the distance between two consecutive identical points.
Okay.
Such as two crests of a transverse wave, right? The wavelength is represented by the Greek alphabet lambda, which looks like this.
Ooh, okay.
Looks cool, huh?
Yeah.
Or you could just do this to keep it simple. You don't need like the curve and stuff. Right? This is the very proper way of making it. But
Stylish.
yeah, but just you can just do that.
Okay.
Then you've got frequency. By the way, is Haram back?
Yep.
Because I heard the ting.
Yeah.
Frequency is the number of waves that pass a point per unit time. What does this mean? Right? Basically, in other words, it is the number of complete waves per second. Number of complete waves generated per second. Okay, so that's what the frequency is. And it is given as hertz.
Herds.
Hertz, right? Or Hz.
Yeah. Okay.
So if, for example, a wave has a frequency of 2 hertz, that means it is generating, the wave has two complete waves per second. What's a complete wave, right? So if we go back over here, this thing, one crest, and so starting from the, well,
Starting point.
well, yes, right, the what's it called? The mean position, mean position. You have it going up with a crest, coming down with a trough, and then coming back. So this whole thing over here is one complete wave.
So it's 2 hertz in total.
So this would be 2 hertz, for example.
Yeah.
If the time over here is 1 second, so this is 2 hertz, having two complete waves within 1 second.
Yeah.
Okay, and similarly for sound waves as well, right?
Okay.
So you have a complete compression and a complete rarefaction. So this thing, this whole thing over here is one complete wave, a compression and a rarefaction.
Okay.
Okay, then from the
Yeah.
next compression onwards to the next rarefaction, you have the second wave.
Okay.
Okay,
Could you go back?
yes,
Yeah, you said from compression to rarefaction, it's one complete wavelength, right?
one compression and one rarefaction.
Why didn't you start from before compression? There's still rarefaction there.
I started from the, oh, this one. I mean, you could do that. Yeah, sure. It doesn't matter.
Oh, okay. Okay, I thought you did that on purpose.
Yeah,
Okay.
right. Point is that one compression and one rarefaction, one completes the right. So
Completes the wavelength.
yeah, this is one complete wave,
Okay.
right? A crest and a trough. So crest plus trough
It's one complete
is
hertz.
one wave, one complete wave, not one complete hertz.
Yeah.
Hertz is frequency which tells you how many. So you can have, right, 500, right, megahertz, which means there are 500,000 waves per second,
Yeah.
right,
Okay.
which is a
Yeah.
lot,
Yeah.
right? So if you have like a radio, right,
Hmm.
the right, the radio channels that you tune into, right, they have hertz. So you're listening to 98.4 FM, right, and that's basically the frequency of the channel. So that's 98.4, right, hertz or megahertz or kilohertz or whatever it is. So that's the frequency of the sound wave.
Oh, okay. Okay.
That is the frequency of sound wave at which that radio channel, well, actually the radio wave, not the sound wave, right? Well, yeah, so right, at which the radio channel is being transmitted. Okay, so radio wave basically.
Okay.
So where was I? I'm sorry, I'm a bit, you know, I'm not
Yeah.
I'm not at my
Next
best
one.
right now.
Frequency.
Frequency. Okay, so amplitude, I've talked about that. And right, it is the height of a crest or the depth of a trough. Uh, right, measured from the undisturbed position. Right, so again, if you go back to this, what's the undisturbed position? This particle over here, right? It's sitting at the mean position, right? It's at the starting point. So it has like it's not being moved up or down, right? So from this point to the maximum point for the crest, or the minimum point, either of these can be amplitude, right? So it's not just the crest, it's also the trough. So either of these are the amplitude, because you would have the same amplitude for the crest or the trough, right? It's the same. It's not like crests are higher and troughs are lower. It doesn't work that way with waves. Okay?
So they're both equal.
They're both equal. Whether you measure the maximum displacement from the crest, right, of the crest, or the maximum displacement of the trough, right? Either
Yeah.
of these, you'll get the same value.
Yeah. Okay.
Okay.
So like draft and crest are the same thing.
They're not the same thing, because the crest is the high point and the trough is the low point of the transverse wave,
Oh,
right? In terms of how much, how high, and how low the trough is, so that the magnitude of their displacement, right, is the same. The magnitude, meaning how much. So if the crest, for example, right, is, let's say, 5 millimeters, right, then the trough will also be 5 millimeters. So in terms of the value of their displacement, again, I keep repeating displacement, because right over here you have magnitude plus direction, right? The crests are moving up, the troughs are moving down, right?
Yeah.
So it's a vector. So the value, right, the direction is different, but the magnitude is the same.
Okay. Yeah.
Okay.
and like distance between these are wavelength.
No, distance between two consecutive, in the case of a transverse wave, right? The distance between two consecutive crests or two consecutive troughs, either of those, right? That is a
Yeah.
wavelength, because that would make one complete wave. So it's going up and then it's coming down. So that is one complete wave, right?
Yeah.
Okay. Uh, I'm going to stop here, because right, I feel like I'm losing my focus. So
Yeah.
I had planned on completing it. It's an introductory chapter, so it should be a breeze, but that's not how it's going, and we are also out of time. So I'll see you guys next class, right? If you
Okay.
could read ahead, that would make explaining it easier a bit. It might be a
Okay.
bit vague, but just read to the end of the chapter, right? So they talk about reflection and refraction and diffraction and all of that. So it would help with the explanation. Once we're done with that, obviously we'll move on to talking about light. Any questions about Haram? Right? What was your question? Do we have time? I believe we have a
Like
few.
it is kind of like dumb, but what exactly are waves?
What exactly are waves? That is actually a good question, right?
Oh,
So, so a wave is a disturbance that transfers energy, right? So let me write that down. Something probably that should have come at the start of the chapter. Of course, we don't have space to squeeze it in over here. So, what is a wave, right? It is a disturbance, and by disturbance, it means that something is put into motion. It's moved, right? So, if you're sitting and someone like comes and tells you, oh, get up and do this, and you're like, why are you disturbing me? And that's how particles or energy feels as well. They're like, chill, like, no, move. So when they start moving, that's a disturbance. So it's a disturbance that transfers energy, right? Now, this could be because we've got mechanical and progressive waves. So this could be either through a medium, which means matter is involved, or space, right? Without matter. Okay. So that's
Yeah.
that's what a wave is.
Okay.
Yeah.
All right, Hera?
Yes.
Okay. Thank you for that question. And on that note, let's end today's class.
Okay.
So see you guys next time, and
Allah Hafiz.
do read ahead.
Okay.
Allah Hafiz.
Allah
Okay.
Hafiz.
Allah Hafiz.